All right, hello everybody. This is looking at the vertical environment of lakes. So basically what we're going to do is see how different variables change as we go deeper into a lake. So we're kind of going to concentrate on three different parameters: light, temperature, and oxygen. Now, all of these things basically impact one another, okay? So, and life then can change these things too, right? So we know how temperature controls oxygen, right? Colder water has more oxygen, but oxygen can determine what type of life is living where, but the biotic and then the organisms can control whether there is oxygen also, whether you have plants there doing photosynthesis or respiring. Light then determines what type of organisms there are there, but you only find algae at the top of the lake because that's where the light is. But if you have too much algae, that can shade out light. Light controls temperature. Light, in the grander sense of looking at infrared radiation, controls temperature, and then temperature can control what type of organisms live. So all of these things are an interacting web, and we're going to kind of talk about each one individually and then how they interplay a little bit. So, when we think about a lake, remember we have that littoral and limnetic zone. We're kind of going to be out in the limnetic zone, out in the deep water. And out in the deep water, what you have is a photic zone and an aphotic zone. The photic zone is, that portion of water that has light penetrate. And when I say light, what I mean is basically we have to draw a line of where there's only 1% of the incident light, because light will bounce around and there is light at the bottom of a lake, but just very, very little. So at the point where there's about 1% of incident, that means of the light that actually hits the surface of the water, where you have 1% of that remaining, that's where we draw the line, and below that is the aphotic zone. And what we find is in the aphotic zone, there's essentially, no living algae. No algae that are photosynthesizing. Okay, there are some algae that can go down there for a short amount of time, but those are vertically migrating ones. So yeah, we're going to be thinking about the photic zone and the aphotic zone. So let's begin thinking about light, okay? And when we're talking about light, remember we're talking about the entire electromagnetic spectrum, from radio waves all the way up to microwave, infrared. That visible light is only a very small portion of the electromagnetic spectrum, right? And so we're going to kind of really only be concentrating on infrared through ultraviolet, because that pretty much is the only, biologically active portion of the electromagnetic spectrum. X-rays are very minimal, and gamma rays are pretty much non-existent, at least at you only find X-rays and gamma rays pretty much out in space, right? So what we see is, given our sun, our sun throws off a lot of different wavelengths of light. So what we've got here is ultraviolet light, visible light, and infrared light. Okay, and what we see is basically, if you were to take a spaceship and go outside of the atmosphere, this dotted line is what we would see for what the sun actually gives off, right? Now, and what we can see is the peak of that is in this shorter infrared wavelengths. Okay, but then this solid line is what we get at sea level. Okay, so realistically, what hits us where we are on most portions of the Earth, it's a little bit of UV, a lot of visible light, and some decent amount of infrared light. But the different wavelengths are absorbed by different gases in the atmosphere, so that's why it's all kind of up and down here. So the angle of incidence, basically the angle at which the light beam is hitting the surface of the water makes a big difference. Okay, and so when you look at this graph, what we see is surface reflection on the x-axis and the angle of incident light. I feel like this graph should be flipped, but essentially, when you have light that is essentially at 90 degrees of the surface of the water, so this is, think about it like a bowl of water and put a flashlight directly above it, okay? And essentially, pretty much none of it gets it's reflected at all. It goes into the water. But if you have a real shallow angle, so you like take a flashlight and put it way over on the side, and it just kind of glances and on the surface of the water, a lot of that reflects. So here we have, at a maybe a 5-degree angle or something, we get over 80% of the light reflecting off the water. So this is going to, make a difference during the time of day. So at sunrise, when the sun is, just real shallow in the horizon, most of that light is just going to bounce off the surface of the water. Same with, latitudes. The higher latitude you're at, the more light is going to bounce off the water. And then with the season, right, the more wintry you are, the more light is going to bounce off again. So then what we see is waves will make a difference too. So basically what happens is that waves just increase the amount of reflection, because there's just kind of moving all over the place, and the water then gets riled up, and more of that water then more of that light gets reflected back into, up into the sky. So if the light then penetrates into the water, what we see is most of that light is transformed into heat in the first meter, right? We don't usually think of, a flashlight having heat. But little trick you can do is take a Sharpie and draw on your skin a little bit and let it dry out, and then draw again. Make sure it's a black Sharpie, okay? Then take your phone and turn your flashlight on to the highest setting and put it on your skin. Okay, I'd only do this for a very short amount of time, but what happens is that light is actually relatively bright, and it'll start to burn you. You'll feel it. It'll feel like someone's poking you with a needle or something, and it can actually burn you. And so light is energy, right? It's a form of energy, and when it hits matter, whether it's water or your skin, it can turn into heat. Okay. Now it just turns out that a flashlight doesn't have that much energy, but we know that our sun definitely does. Okay, and what we see is infrared infrared light and ultraviolet light really don't make it very deep. They make it about 1 meter, 3 feet into that water, and it's all pretty much been absorbed by that time. Okay, now what we see then is the longer wavelengths of light, like red, orange, and yellow, don't have as much energy, so they get absorbed relatively quickly. And blue light and violet light have a lot more energy. They're shorter wavelength, wavelength in the electromagnetic spectrum, so they have more energy, so they can penetrate deeper. Okay, they get scattered more, but it's a weird property of water that even though violet light has more energy than blue light, it doesn't penetrate as deeply, just due to the properties and molecular structure of water and the electrons in that water, but don't really want to get into that. Okay, but blue light travels the furthest. Okay, so when you see this ice here, ice pretty much has the same absorption spectrum as liquid water. This light here, these big ice blocks look pretty blue, is because as that sunlight is going through this block of ice, the red gets absorbed, the orange gets absorbed, the yellow gets absorbed, the green gets absorbed, most of it, and the purple gets absorbed. So most of the light that comes through is just kind of this greeny bluey thing and looks really, really blue, and that's why essentially water is blue. Now, sorry, let's go back here. See this red, okay? Red sunlight, whether we're talking about fresh water or salt water, basically doesn't make it beyond 15 feet. All the red light is absorbed, okay? So red color at depth is effectively invisible, okay? So if you look at this picture here, this is like a cloth, a piece of cloth. So this is with natural light here. So this picture here is with natural light, and this and then this is they shine a flashlight on. And I've done this while scuba diving. It's pretty crazy. If you take like a rainbow board down deep, those colors like disappear. They just look like brown or look like anything else around. And it's effectively invisible. It blends in. It doesn't reflect any light, so it makes it actually relatively hard to see. So it only turns red because this flashlight, when you're shining on it, has some actual red light in it, and then that shirt can then reflect that red light back at you. So what we see is that really down deep, and a lot of deep sea organisms are red in color, and that's because they can camouflage themselves relatively well. That red pigment makes them, there's no light to actually reflect off of them down deep, so they're very hidden. So predators can, be better predators, and prey can hide from predators better that way. So it's like overrepresentative that deep sea organisms are red. Whereas an organism, if it were to be blue, it would be really visible, and that wouldn't be as good of a strategy. I'm going to skip this. Okay, so what happens to heat then? Okay, most of the heat is transferred in infrared light. Okay, so when you are sitting next to a fire, and if you're 3 or 4 feet away and you put your hands out, you can feel that heat hitting your hands. And what that is actually infrared radiation. Okay, infrared radiation transfers heat really, really well. Okay, so this picture here is a picture of an infrared picture of Madison, right? So, oops, that didn't make an N. Well, Madison is right in here, right? So Lake Mendota and Lake Monona are right here. And what you can see is the ground does a really good job of reflecting a decent amount of infrared light. However, these lakes here are black holes, essentially. Water does such a good job of absorbing infrared radiation such that it just completely absorbs it all and doesn't let anything reflect. That's why these appear black here. Okay, the thing is, it's only at the very tippy top of the water, basically the first 3 feet. Okay, so if you want to heat the water below 3 feet, essentially what you need to do is move that water. Okay, the water will not, the light won't heat up any water deeper than about 3 feet. Okay, so you got to stir up that water to heat the rest of the lake. When you dissolve things in water, then it can really change how light interacts with that water. So dissolved organic compounds, basically any organic material in the water, including like humic acid, tannins, the things you get from that tea-colored water that you get in, northern Wisconsin next to pine forests, basically. Those will really allow for absorption of, in particular, UV light. So go back to here, and what we see here is UV light is pretty much all gone within, again, that first meter of light. Now this is like natural water. If you were to take distilled water, so just looking at pure water, UV light goes through it really well. But if you have just a tiny little bit of organic material in it, it absorbs that UV light really, really well. So What you might notice sometimes is in certain lakes, you get these really brightly colored copepods. So these are copepods here that are red and yellow and orange. Essentially what we see is these are not deep water copepods that are like trying to hide, right? These are found just up near the surface. And there's this interplay then between having pigments to essentially avoid getting sunburn, but also being really clear colored to avoid being eaten. Okay, so here is a Daphnia, right? And this Daphnia is really transparent. And the reason that's transparent is probably this lives where there's a lot of zooplanktivorous fish. And like pretty much the only non-transparent thing is its intestinal tract, which is right here, which is full of algae, and then its egg sac here in this carapace. But it's transparent to avoid predation. Okay. The thing is, if this is up near the surface of the water, UV light that hits the water and it gets into the water, it can essentially attack any portion of its body, and it's going to basically be like radiation attacking any organ that it can possibly see or reach in that Daphnia's body. So if there's really, really clear water, in the absence of predators, this being clear is not very good. So what we see is in really, really clear water with no zooplanktivorous fish, you get red zooplankton. So basically they have a suntan and they can absorb that UV radiation and they don't get skin cancer. Okay? But if you have really, really clear water, but also predators, you get clear zooplankton, because there's this trade-off between basically, do you want to get skin cancer or do you want to get eaten? And what natural selection has basically chosen for these things is that they would rather get skin cancer, right? Because predation is a bigger threat to them. So, but if you have water that's like this, there's really already a bunch of organic substances in it, and all the UV radiation gets absorbed in the first couple inches, then you find clear zooplankton because they don't need to worry about UV radiation. They'll just be clear and be fine, and then they're also protected from predators that way. So put together a little chart like clear water, organic compound water, like tea-colored water, and then predators are not, and then you can write what color the zooplankton would be expected to be. I've found some really, really cool, really dark, really interestingly colored zooplankton in fishless wetlands that, you can see these really big copepods that are super bright red and stick out, but they just don't get eaten because there's no fish in the pond. So it's a pretty cool system. Okay, what about light with ice? Okay, this is at Lake Baikal. This ice is really, first off, the water is extremely nutrient poor. There's essentially no algae in it, and it makes really, really clear ice. Lake Baikal is famous for having this really clear ice that people go out and visit all the time. And if you have this type of ice, or this ice has cracks in it, but it's still a lot of clear, thick ice, but light goes through it no problem, right? You can see this person even though this ice looks to be about a foot thick. Okay, so light can go through ice relatively well. However, if you have ice like this that is, has a bunch of bubbles in it or organic compounds in it, it does a pretty decent job of scattering and absorbing that light and doesn't allow light penetration as much. Snow obviously increases light reflection, right? I wear sunglasses more often in the winter when I'm, outside and there's a bunch of light reflecting off that snow. So, but light still does go through, right? If you were to make, I've made plenty of snow forts where you cover it completely in snow, and there's still plenty of light that can get into that snow fort, relatively no problem. But if you have like a really big ice layer with a bunch of snow over the top, oftentimes you get these winter kill events of fish because there's essentially not enough light going into that water to not power photosynthesis, and then the lake essentially runs out of oxygen. That can happen if you have a real thick snowpack. Okay, let's shift now to temperature. So temperature is tied to the sun, right? Like, doesn't really matter what type of water it is. It's pretty much just in the summer the water's hot, in the winter the water's cold. What we see is that heat doesn't really move into the sediments or out of the sediments very much. I mean, unless you have like lava or something, it's not really going to change. That there's not going to be any heat exchange. Maybe a volcanic lake in a caldera would have some geothermal heating, but that's relatively rare. So essentially, in most lakes, especially all glacial lakes, essentially all of the temperature fluctuations happen at the surface of the water. Okay, so heat gets absorbed from the sun. And then heat either gets exchanged with the atmosphere, depending, if the atmosphere is warmer, heat will go into the lake. If the atmosphere is colder, heat will go out of the lake. So, what I want to talk about, though, is how the temperature affects that density. And remember, as a recap here, we have increasing density as water gets colder, and a density peak at about 3.94 degrees Celsius. The water then gets less dense as it approaches 0 degrees Celsius, and then it jumps as it freezes because of the crystalline lattice of those water molecules becoming essentially permanent. Those hydrogen bonds become permanent and spread the water molecules out and make less dense ice. Okay, so what this causes is lake stratification. So what we see is as you heat the top of the water in the epilimnion, you create a warmer portion up top, and then you get the metalimnion, which is the area of most change of temperature, and then the hypolimnion, which is the stable, pretty much water that is all at 4 degrees Celsius. Now you can get stratification due to differences in salt concentrations. You can get it, but the most common thing is with temperature, right? You don't need that much difference in density to create a really strong stratification. And when you get stratified water, then it really resists mixing. So, if you get wind going across the top of the lake, the stratification pretty much only stays within, maybe I should change the color of this to green. Okay. The stratification causes, circulation only in the epilimnion. Okay. Remember that epilimnion is that basically the part of the water that is warm, and then the metalimnion is where it drastically changes temperature, the area of biggest temperature change, and then the hypolimnion is below that metalimnion with stable temperature. Okay, so the wind that is blowing across will only mix the epilimnion. If you just have a couple degrees difference in water temperature, it'll cause stratification then. So this is a really interesting picture. It looks like this diver is coming up out of the water, but actually you can see these are bubbles here. They're still underwater. This is salt water underneath, and then overlaying it is some fresh water. Here's another picture of a diver. Looks pretty freaky, right? But here You know, below this line, this is all salt water. Should switch back to red so you can see it better. And then this is fresh water up here, because the fresh water is less dense, right? And you can, the density differences here are so strong that even a diver swimming through it won't break up that, that stratification. So, most lakes in the northern hemisphere have this, you know, this strong epilimnia and metalimnia and hypolimnia in the summer. And then what we see then is most glacial lakes are these dimictic lakes. Okay. Next lecture we'll be talking about amictic lakes and polymictic lakes and monomictic lakes, but I want to talk about a dimictic lake here. We'll spend some time on it in a second here. Oh, I forgot. Here is where I define what an epilimnion is. Epilimnion is the upper stratum of a lake. It's well mixed, right? The metalimnion is a zone of steep gradient. Now that's usually temperature, but it could be salinity. And then the hypolimnion is that lower stratum of constant temperature. So this graph, spend some time thinking about these graphs and these diagrams, because it's really important to understand what's going on in a dimictic lake. So what we're going to do is we're going to start thinking about this spring, okay? Let's say the ice has just melted, and what happens is the water is at 4 degrees Celsius. And remember, it's at 4 degrees Celsius because that is the lowest density of water. And so, you know, at the bottom of the lake, you've got 4 degrees Celsius. At the top of the lake, you know, in midwinter, it'll be lower than freezing. But then once the ice melts, all of that water basically gets to be 4 degrees Celsius. Okay? So what you have is a constant temperature at that, you know, 3 or 4 degrees Celsius. And the dissolved oxygen then is really high up here at like 12 parts per million, okay? And because the water is continually mixed, there's no stratification, there's no differences in temperature, therefore no differences in density, so there's no stratification, and a little bit of wind will keep this lake mixing and circulating. So depending on the size of the lake, the larger a lake is, the more that lake will mix up. Basically just because the fetch is longer, so you get more wind action on that lake, and it can make a more powerful mixing. So as you get then from spring into summer, if you have a really windy spring, the lake will kind of all warm up together. So, but remember, in early summer, the sun starts to get stronger, and that top layer is heated. Remember, the top layer is heated only because the that infrared light is absorbed in the very upper, you know, for really the first couple inches. Okay. Now, if you have a calm day, then just, you know, you need 1 or 2 calm days, and it'll start that stratification process, and you get really warm water up towards the top. And then, you know, at the bottom of the lake, it'll be 4 degrees Celsius. Only just a few degrees difference, maybe just 1 or 2 degrees Celsius difference, will prevent that lake from circulating and mixing anymore. So the bottom layer then stabilizes at the maximum temperature reached during the spring turnover. Realistically, this is pretty much always 4 degrees Celsius, but if you were to have like a really, really windy spring, it could maybe get up to 5, 6, 7 degrees Celsius. So the depth of then thermocline, so how far deep this, you know, the epilimnion is really dependent on the lake size and how much wind there is. So in a really windy spot, in a big lake, big surface area lake, not necessarily depth, the deeper that epilimnion will be, just because there's more wind action working on it. So what we see is this stratification continues through the summer. Okay. And by late summer, you get a really, really strong stratification, and it's rarely disrupted. So if you were to have, a normal sized lake and maybe a 100-mile-an-hour windstorm, you can disrupt that stratification. I've seen that a couple times where a lake gets really cold after a big storm, but we're talking like literally 100-mile-an-hour wind for several hours. It would take that much wind action to break this stratification, and humans can do it with big machines, but it essentially doesn't work very well. So as we then get into fall, the lake stratification essentially starts to break down. Now why? Essentially, there's still sunlight during, in let's say in September, October, there's still sunlight going into the lake, but heat loss is radiating out, the water is evaporating, so it's losing a lot of heat, and as soon as that heat loss exceeds the heat input, the lake starts to cool down, and that cooling happens at the surface, and eventually, so you go from, this, let's go back to this picture, right, where you got 22 degrees Celsius water, and what happens is that, during a cool night, the surface of the lake starts to cool down, and it gets to 21, 20, 19. Well, as soon as that happens, then it gets denser, and that will fall down. The gravity will pull it down, and it'll mix within the epilimnion until the epilimnion becomes again 4 degrees Celsius. So in southern Wisconsin, what we see that this lake would be 4 degrees Celsius by mid-October or something, okay? Now, the largest of the lakes, like Lake Superior, will stabilize here at 4 degrees Celsius, around 39, 40 degrees Celsius all winter. So Lake Superior, parts of it can freeze over, but the middle portion of the lake never really freezes over, and that's because there's essentially so much heat in that water. It just never cools down that much, and there's enough wind action to just continue to mix all of that water, such that it would never really get cold enough to freeze the entirety of Lake Superior, unless we're in a glaciation time, but that's different. Then in winter, what we have is this reverse stratification. Actually, you get colder water on top of warmer water. Okay, and that's because of this 4 degrees Celsius water being the densest, and then, let's say 0.1 degrees Celsius water, right? That's almost freezing. That water is less dense. So as, the top layer of water continues to cool down and eventually freezes, so let's say, the water freezes and you can have ice at, negative 10 degrees Celsius, but then right below that, right below the ice, you'll have essentially 0 degrees Celsius water, and then it'll warm up as you go down a little deeper to 4 degrees Celsius. So what you see is this temperature starting at 0 and then going up into 4, and then that dissolved oxygen is going to follow that too. So for ice to form on a lake, you just really need one calm night. And it's really interesting. A lake can be the whole, the surface of the water can be below freezing, but because of the continuous movement of that water, it doesn't let the crystalline lattice form. So you get one calm night and the lake can freeze over, right? It's interesting kind of phenomena where you can get, overnight 3-4 inches of ice just because the first 3-4 inches of water was already below freezing, except the wind wasn't allowing it to continue to form that crystalline lattice. So once you get ice, it seals that lake off from the mixing power of the wind, and you can have this stratification. So even though the stratification, these density differences between the 0 and the 4 degree water are not that strong, it can because you have no wind action, it will create this reverse stratification. So think about the temperatures and how these are changing through a season, and this will help you. I would draw these graphs and these little diagrams a couple times so that you can understand what's going on. I always like to start with spring because it kind of makes sense that, as soon as that ice goes away and the water's all 4 degrees Celsius, that's a good place to start. All right, so I haven't really talked that much about oxygen yet. So here's where that's going to happen. Okay, so we know that air is about 21% oxygen. It's more soluble in water than nitrogen, so you can have higher concentrations, somewhere 25-30% oxygen in the water. But this is mediated by a couple things. So pressure, so elevation, you'll have more oxygen at a lake of the same temperature at sea level versus at higher altitude. Basically, just like as you go up a mountain, you get less oxygen. You get less oxygen in a lake too. Salinity. What we see is seawater is always lower, and the reason you can think of that is seawater has less oxygen, essentially because there is the dissolving capacity of water is taken up by the salt. So, but what we see is temperature is still the most important factor here. Remember, the colder the water, the more oxygen. So the colder the water, the more oxygen you get. And oxygen is really important based on, or is really changed based on the trophic status of a lake. So depending on how many nutrients are in the lake will really change how oxygen gets the oxygen dynamics of a lake. Okay, so an oligotrophic lake is a lake. Oligo means few, and trophic means food, so it's low nutrients. And these are low productivity lakes. Think of them as just pretty much pure water, right? So Lake Superior here is really clear. Lake Michigan is actually the clearest. Right now, it is the clearest Great Lake. Didn't used to be. But eutrophic then are, this green water lakes. High nutrients, high productivity. So add a bunch of phosphorus to a lake, you get a bunch of algae growing. Then mesotrophic is, lakes more, this is more common like most of the lakes around in southeastern Wisconsin because there's some human impact in them, adding some nutrients to them. But somewhere in between, the lake is relatively clear water, but still kind of has a green tint to it. Okay, so think about temperature. Okay, this is the temperature profile of a lake. So here we have the surface of the lake, right? And then as you go deep. And so we've got the epilimnion, then the metalimnion. So the epilimnion, the metalimnion, and then below that, the hypolimnion, right? So it gets colder. So this is cold here, and this is hot, right? So you get that colder as you go down in the lake. Now, an oligotrophic lake will show this pattern, okay? Because there's little decomposition, essentially it's pure water and there's not really life in it, the oxygen dynamics are governed by abiotic factors. So, warmer water has less oxygen. Colder water has more oxygen. So you get this, reverse pattern, basically showing that there's a bunch of, even though it's at the bottom of the lake, because there's no real life going on in there, you get just physical properties of that colder water having more oxygen driving what happens with the oxygen dynamics. Eutrophic lakes then will be very different. Okay, oxygen is governed by biotic factors. Here you have high decomposition, high amounts of respiration, and you have a rain of organic matter going into the hypolimnion such that there's a lot of decomposition down at the bottom of the lake. So you only find oxygen where algae are actively producing it, and that's only going to be in the epilimnion because that's the only spot where the light is. All of these algae up here, essentially shade out all of the light below it, so you don't get any light below into the meta or hypolimnion, and then no photosynthesis, therefore no oxygen. So when you look at this, these graphs here, you can see that at the spring turnover, it doesn't matter whether we're in a oligotrophic or a eutrophic situation, dissolved oxygen is high throughout. In the summer, then, you get that same pattern of high dissolved oxygen at the bottom of an oligotrophic lake. See, here we have oligotrophic up top here. And then in a eutrophic lake, you get that pattern of essentially no oxygen in the hypolimnion because there's no light down here. Only photosynthesis is happening up top. Fall is just like the spring, no matter what we're talking about, oligotrophic or eutrophic. And then in the winter, in an oligotrophic lake, you have colder water having more dissolved oxygen, and then it's pretty much, just a couple inches below the ice, you're going to get a lot of dissolved oxygen that's stable throughout the whole thing. Whereas in a eutrophic lake, remember the water is colder, so dissolved oxygen will be, further to the right here. There'll be more dissolved oxygen. That's why we see, the curve here stopping at about 8. So we're stopping here at about 12. But you still have that down here, that high amount of decomposition even through the winter, and there's no light down here, such that you don't get any dissolved oxygen. So draw these graphs. If you can understand what is happening in these graphs and which line means what and why it is where it is, you'll understand pretty much this whole lecture. You can kind of integrate the entire lecture into these graphs right here. So again, this is kind of, sorry, I forgot that I had the slide. This is showing that in eutrophic lakes, you get anoxic conditions in the summer and in the winter, right? Kind of depends on how much snow and ice there is, but you get, fish kills oftentimes in these type of eutrophic lakes because they're because of these oxygen dynamics. And the longer the winter is, basically this, this line will start to just continue to go down and down and down until there's not enough oxygen for those fish to survive anymore. What I didn't really talk about is the sediments. Really, whether we're talking about a eutrophic lake or an oligotrophic lake, the water in the sediments is generally anoxic because there is some amount, even in an oligotrophic lake, there is some amount of bacteria in those sediments, and they will eat up all that oxygen, and there isn't enough freshwater flux into there to to bring in more oxygen, so you have anoxic conditions in those sediments. All right, with that, I'll see you later.